All right, welcome to another Calculus 2 integration methods video. Today we'll be talking about trig integrals and a special kind of process we use for them when they're not just kind of a standard U substitution format. So I'm going to go through first one that would be a standard U substitution, and then we'll compare that to a trig integral problem, and you can see that there are similarities, but there are also differences. And because we're still going to be using U substitution, we just kind of have to vary it slightly and use a very specific process to get the problem done. But it's not too bad to do. So this problem here is a standard U substitution problem. The way we know this is we have some sort of function to a power, and we have its derivative over here that we could cancel with the du once we do that process. So if you forget, how that works is we're going to make the u the function that's within a function, so the sine to the fourth x. So u equals to sine of x, and we'll say that du, so the derivative, is equal to sine's derivative, which is cosine of x dx. Then we would divide by cosine to get the dx alone instead of the du, so we get that dx is equal to du over the cosine. So this was just dividing this and then dividing this. If you're a little unfamiliar on U substitution, there's other videos talking about U substitution. It's not too bad to do, but this is kind of the general process. So now we have this. We're going to kind of take this function, right? And we're going to say the integral of the sine. So we said u is sine. So we're going to replace sine with u. So this is sine to the fourth. So it would be u to the fourth. That makes sense. We're going to keep the cosine. Then we're going to have the dx is equal, so this is equal to du over the cosine of x. Now, because this is like cosine over 1, these things will cancel with one another. They'll turn into just 1, so we can cancel them. So now we're left with the integral of u to the fourth for du. And now we can do this. This is a standard power rule problem, so we're just going to increase the power divided by that new power, which is u to the fifth power over 5, and of course we're going to have that constant of integration c, and then we just have to put our u back from what it equals. So it equals sine, so we're going to just put sine in place of u, so sine to the fifth of x over 5 plus c, and that would be our answer for a standard U substitution problem. So now we're going to compare this to the new process I'm going to teach you, which is the trig integral problem. The reason you'll know it's a trig integral problem is because we won't just have the one function to a power and then the derivative here. We'll have a function to a power and then another, its kind of derivative-ish function to a differing power, and we can't just use standard U substitution. So what we do is when we see this kind of look to them, we want to look for the function with the odd power, okay? Or if they're both odd, we look for the higher odd power, but if it's just one of them, we just look for the odd power. And you'll see why we want to look the odd power in one moment. So what we're just going to do, that's all we're going to do right now, is we are going to take off one of the signs, right, from this fifth power, and just multiply it around, which won't change the value of the function. So if we had sine to the fourth of x times the cosine squared of x, and we're just going to put this sine of x right here, okay? Just this is the same thing, we're just rewriting it. Okay, so what we want to do with all of these problems is we want to find a du, so a derivative of a function, that will cancel with the thing we took off so that we can use U substitution, okay? So the best way to think of it, I think, is usually we say, okay, we have a u, then we have a du, right? So that's not going to change. But this time we actually know what we want the du to be. We want it to be the sine of x we took off, okay? So we're just going to say the du should be sine of x dx, right? Okay. So if we had a function here, what derivative would we have to take to give that function? So we know that sines would be cosine, cosines would be sine, right? So cosine of x would be negative sine of x. Don't worry too much about the negative, okay? So the negative isn't really very consequential. So we're going to put the negative here because that's technically true. The derivative of cosine is negative sine. And then what we're going to be doing is, now that we have this in place. We know what the u is, we know what the u should be, we know what the du is going to end up being. We have to, okay, the u is going to end up being cosine. So we need everything to be in terms of cosine, right? So that then we can make everything in terms of u and solve this just like this u substitution problem, okay? So what we need to do is we have to use the trig identity for sine and cosine to turn the sine function into cosine. But the first thing we're going to do is we're just going to rewrite the sine to the fourth as sine squared times the sine squared of x times the cosine squared of x times the sine of x dx, okay? So what you'll notice is now we wrote them in square. The reason we did that is because we know the identity that the sine squared of x plus the cosine squared of x equals to 1. And what we know very easily is if we minus either one of them, the sine squared function will equal to 1 minus that other function. So for example, sine squared would be equal to 1 minus the cosine squared if we subtracted it to the other side. So knowing that, we're just going to sub that identity in. So these two sine squareds can become 1 minus the cosine squared of x. So 1 minus the cosine squared, 1 minus the cosine squared. That's all we're doing. We're just replacing it with the equivalent form. That's all. And then this cosine squared of x, of course, stays. We're still going to keep the sine, and we're still going to pay the dx. So now everything but the sine, which we know is going to cancel once we use u substitution, is in cosine. So we can just go ahead and put u's now. Now don't forget though, the 1 will stay as a 1. So 1 minus, because it's just a constant, this is u squared, right? And then 1 minus u squared again. Now this cosine squared is just u squared. And then the sine of x was, of course, stays just like u substitution. And our du, if we divided the negative sine of x, we would get that dx equals to du over negative sine of x. So du over negative sine of x, right? We're just solving for dx. That's all we're doing. Just like this one, we're just solving for du, for dx given du. That's all. Okay, so now we can cancel these signs. Remember though, we do have this negative here. So we can keep it in the problem, but it's much easier just to move it all the way out to the outside, which is something we can do in integrals, okay? Next, we're going to have to kind of multiply all this out. So these ones here, we're going to have to FOIL, okay? So if we had 1 minus u squared and then 1 minus u squared, if we did that on the side, 1 times 1 is 1. 1 times negative u squared is negative u squared. Negative u squared times 1 is negative u squared, and u squared, or negative u squared times negative u squared is positive u to the fourth. And if we just combine like terms, these two negative u squareds turn into 2u squared, just kind of adding variables, and then this is u to the fourth. So all of this is this little FOIL we did here. So we can replace it with 1 minus 2u squared plus u to the fourth times this u to the squared. We still have another u squared here from the cosine squared. And then this is just a du because we canceled the signs and we put the negative out here in the front. So now what we can do is we're just going to distribute the u squared to the parentheses here. So what that'll look like is we'll have u squared times 1, which is u squared. We'll have u squared times negative 2u squared. So when we multiply, kind of distribute them, we're actually going to be adding the exponents. It's only when it's, let's just say, x squared, maybe squared, this would be a multiply of the exponents. But over here, this is adding them. We're going to add the exponents. So the 2 will stay, but u squared times u squared will give you u to the fourth, since it's 2 plus 2. And then u squared times u to the fourth, that's 2 plus 4, which is u to the sixth. And now we have a du. And now we've done all this work in substitution, and now it's a pretty nice polynomial to take the integral of. We just can use the power rule. So we're going to have to keep this negative. Don't forget the negative, or else the answer will be incorrect. And we're going to do the power rule for all of these. So u squared, if we raise the power to all of these and then divide by that new power, we'll have u cubed over 3 minus 2u to the 5th over 5 plus u to the 7th over 7 plus c. Negative, since it's a positive here, so negative u cubed over 3, and then the negative times a negative will give you a positive, so plus 2u to the 5th over 5. And then if a negative and a positive turns into a negative, so negative u to the 7th over 7, and we still have the plus c, of course. And now the problem is done. This is the answer, but just like u substitution, we typically want to put the u back in. Now the u in our function was the cosine, so we're just going to go ahead and put, everywhere we see u, we're going to put the cosine in. So that would be cosine cubed of x over 3 plus 2 cosine to the 5th of x over 5 minus the cosine 7 of x over 7 plus c. And this right here is your final answer. So all of this original integral equals to this answer right here. So as you can see, the process will be similar to this each time. It's just going to require a little bit of foresight into what the u and the du should be and a little bit of manipulating. So I'm going to come back with kind of a similar example. Welcome back. We're going to be doing a similar problem, but this time with secants and tangents. You usually will only see secants and tangents, cosines and cosines for trig integral problems typically. To do this, we're going to be approaching it in a very similar way, except we have to kind of better keep in mind the derivatives of tangent and secant. So like before, we're going to just try to pick a u and a du to try this on. Unlike sine and cosine, you can't really just usually pick either or and it probably will be fine. You kind of have to see if it will work with the actual problem all of the time. So we're just going to try one of them. If it doesn't work, you just try the other one. So let's say we want the u to be tangent of x, which means the du would be secant squared of x dx. Okay, so do we have like that kind of, can we take out something like secant squared? Because we know the du has to be secant squared, so do we have a secant squared we can take out? And we do, right? We can go ahead and take out a secant squared from secant to the 4th of x. We'll keep the tangent the same, which will mean we'll have secant squared of x and then dx. And then if we wanted to get this in terms of the tangent, so the u needs to be tangent, so how would we do this? Well, we would know the identity for secant and tangent, which happens to be 1 plus the tangent squared of x equals to secant squared of x. So we need it to be in terms of tangent, so we need secant to turn into this 1 plus tangent squared. And look at this, we have a secant squared, so we can totally do that. So secant squared turns into 1 plus tangent squared of x. We're still going to keep the tangent squared of x, and we're still going to keep the secant squared of x, and then we're going to have a dx. Okay? Now we know that we have kind of everything in place. Everything but the secant squared is in terms of tangent. So we're just going to go ahead and solve for the dx, which means just like before, dx would equal to du over to the secant squared of x if we just divide by secant squared. Now that we have that in place, we kind of can turn everything in terms of u for our u substitution. So tangent is our u, so 1 plus u squared here. This tangent squared turns into u squared. We're going to keep the secant squared on the outside. The dx is equal to du over secant squared. So we can go ahead and cancel our secant squareds, as we knew we would be able to, kind of manipulating the process. Now we're going to be left with 1 plus u squared over u, times u squared du. Now we don't have to FOIL anything, we just have to distribute this over. So this u squared times 1 gives you u squared, and u squared times u squared, the exponents add, they give you u to the 4th times du. Now we can easily take the integral of this power rule. We're just going to say this is u cubed over 3 plus u to the 5th over 5 plus c. And finally, we're just going to put tangent back in. So tangent cubed of x over 3 plus tangent to the 5th of x over 5 plus c. So as you can see, this would be our answer to this expression here. The process is pretty similar to the sines and cosines. You just have to be aware that the derivative of tangent is of course secant squared of x, and if we chose the secant route, our dE would be secant tangent, and we would have to take out a secant and a tangent for this to work. Okay, so this was the kind of second example using the standard trig process for integration, and also trying with the secants and tangents. We're going to come back for one last thing with a little bit different kind of unique problem. Come back to this last quicker problem. This is going to take nearly as long as the other ones, but I did want to show you that when we have an even power, if you have multiple even powers, you have to use the double angle formula for all of them, and it becomes a bit of a mess to solve. They usually won't give you a ton of those, and in a future video I might go over its own video dealing with even powered trig integrals, because they're just a little bit more of a mess to deal with. There's a lot of algebra simplification, but I wanted to give you a kind of introduction about what if we have just an integral of an even power. It's not always straightforward what to do. This isn't exactly a U sub problem, but it's important to kind of see this process. So what would we do is we need to use an identity. So the sine squared of x, and this is just a trig identity, is equal to 1/2 times 1 minus the cosine of 2x, and the cosine squared of x, if you had that one instead, is 1/2 times 1 plus the cosine of, not squared, sorry, 2x. And this would be just an identity you just kind of want to commit to memory. Like I said, with harder ones of multiple powers, you have to kind of sub them both in. It becomes kind of a nightmare at times to simplify everything together, but I wanted to give you an introduction for it. So what we would do is we would simplify this sine squared into its formula. So as 1/2 times 1 minus the cosine of 2x dx. And all this, although this seems worse now, we actually can simplify this easier. So the first step is to take out the 1/2. It's a constant, so we don't need to keep it in the equation if we don't want to. This is now cosine 1 minus the cosine of 2x. Now this is not multiplication, it's just addition or subtraction. And you know you can, just like the polynomials, you can integrate these pretty quickly. So you can use substitution here. If you know what cosine 2x, these linear terms, will be, you don't have to. But to show you, if we did it on the side here, the cosine of 2x dx, right, we would have u equal to 2x, which means that du is 2 dx. And if we solve for dx, we get dx is equal to du over 2. Then we would say, okay, it's going to be the cosine of u, and then our du would be, our dx turns into du over 2. We'd bring out the 2, which is just a 1/2, right, since it's over, like 1 over 2 here. We'd bring out this 1/2, then it'd be the cosine of u du. We know the integral of cosine is going to be sine, so this is 1/2 times the sine of u plus c. And then our u is going to be 2x, so this is, if we just kind of keep the 1/2 here, this turns into 1/2 times the, supposed to be a sine of 2x plus c. So a trick is, you can always think of it like it's going to be 1/2, it's going to be sort of the reciprocal of whatever the linear term is. So if it was 3x, it would be 1/3, 5x, 1/5, it will always be like that. You can know that it only works for linear terms, but that's a kind of a shortcut. But if you want to do the work with substitution, that's how it works. Anyway, if we wanted to do this integral, we'd say 1/2. We would know that we would put a bracket here because the 1/2 technically needs to distribute to everything at the end. We know that 1, a constant 1, just turns into x. And then this cosine of 2x turns into 1 minus the sine of 2x, as we went through over here. And then we would just have this plus c. You can put it inside. Just know that your 1/2 is not going to distribute to the c, but just if that helps you remember. Then they're just going to distribute the 1/2 to everything. So this turns into x over 2 minus 1/2 times 1/2 is 1/4. sine of 2x plus c. And this is how you would do kind of an even power one. Like I said, I'm going to have a separate video later on dealing with trig integrals where there's multiple even powers. It kind of requires a long time to do it all, and I want to give a full video to that. But this was an introduction to trig integrals. It should give you a good handle how to do about 90% of them. They're going to be like the first two, the same process for all of them. So hopefully this helped. Thanks.